So hi again. Um, Today our topic is how the power ratings on resistors is going to be relevant for our hobby. um, I have here a metal film resistor, so basically a resistor, and it's a special sort, a metal film it is called, but that does not much to the topic. Does not add much to the topic. And yeah, so the color coding here on this one is, I don't know if you can see it very good. It is from left to right, brown, brown, then comes black, black and brown, black, black and brown, and at the end there is again a brown one and brown. So probably you've heard of this before. There are resistors which have 4 color codes and not only 3. And so the last one is always for the rating. Brown means it is the accuracy rating, and brown means it is a 1% accuracy rating. So and the 4 colors before are just standard numerically coded. So brown is a 1, black is a 0, black is a 0, and as with the 3 color coded resistors, the last one gives a multiplier. So brown is a multiplier of 10 to the power of 1, because brown stands for 1, so times 10 to the power of 1. So what we have here is the number 100 and multiplied by 10. 100 times 10 is 1000. So 1000 ohms resistor we have here with a 1% accuracy, and instead of 1000 ohm, often in the industry it is said as 1 kilo ohm, or also often coded if the manufacturers have no ohm sign in their alphabet, then often it's just written as 1K0, so 1 kilo ohm with no new number after the decimal, so 1.0 kilo ohm. You often see this coding. So that is to what special kind of resistor we have here, 1 kilo ohm, 1%. So we're going to be very close to 1 kilo ohm. And now the special thing is that these also have rating of these resistors have a power rating of 1/4 watt, 1/4 W, and this means 1/4 watt, and this is quarter watt. You can also say to it 0.25 watt, and this is also 250 milliwatt. So this is the power rating, and now comes the big question: okay, does that affect us? How does that affect us, the 250 milliwatt? And for a start, let's think of our standard 5-volt electric circuit, where we have let's say all the 5 volts are attached to or connected to this resistor, and then after the standard formula of Ohm's Law we can say, okay, we have 5 volt we have 1 kilo ohm, and if this 5 volt are connected over this 1 kilo ohm resistor, how many ampere are we going to have flowing through this resistors if the 5 volt are connected over this resistor only? And then you use Ohm's law, and it is Uri. That's how you can remember it, Uri. And then you just have to reposition the formula letters here to solve for I, the the current, and I is then you just divide by R from on this side, so you have to divide by R on the other side. So I is U divided by R, and in our example it is then the current I is 5 volt over 1000 ohms, and that is 0.005 ampere or 5 milliampere. So the question is, okay, why did we do that? 5 milliampere. We know we have 5 volt over the resistor, then 5 milliampere through the resistor. Yes, interesting. But how do we then, and what's it about the power rating of this resistor? And so the power is, in electronics, you can calculate it by the voltage times the current. So it is power P equals voltage U times current I. And so for our example, it is power through the resistor is the 5 volts times the 5 milliamperes, and this is 25, and then milli of what is volt times ampere, and this is the cool thing, this is watt in electronics. So you have 25 milliwatt. And now you can see these 25 milliwatt, they are well below the 250 milliwatt that the resistor can have. So we could have 10 times more power through the resistor, and that would be not harming the resistor. But once we get to there, to the 250 milliwatt, then it would be harmful. And what is this power? In a resistor, most of the power is just spent by being converted to heat. So if you put a lot of current to a resistor, it will heat up. And then if you put too much power through it, then I don't know if you have seen it, there is this kind of smoke that sometimes evaporates from the resistor, and then it's gone, it's broken. And so let's imagine we had not 5 volt, but let's imagine we had 50 volt through the resistor, and then we would have, again, the formula is what current would we have through the resistor. It would start, let's say we have 50 volt now, and we have the current would be again so now 50 volts divided by 1000 ohms, and that is like 0.5 ampere or 50 milliampere. And now the power is going to be this 50 volt times the current, so 50 volt times 50 milliampere, and it is 50 times 50 is 2500. This is 2500. And now what? Volts times ampere is watt, but we have milliampere, not ampere, so we have milliwatt at the end. So what we have is 2500 milliwatts, or 2.5 watt. And that is far above what we can do with the resistor. So in all, applying 50 volt to our resistor would completely destroy it, because 2.5 watt is very much more than 0.25 watt or 250 milliwatt. So that is really a problem here. And so you ask, perhaps you ask yourself the question, okay, we increased the voltage by 10. Why did the power not the power that we had before, 25 milliwatt? We would have expected that when we multiply the voltage of 5 volt to 50 volt from here to here by times 10, then from this 25 milliwatt it should have been then 250 milliwatt and not 2500 milliwatt. So it really is a little bit, the increase in watts in power is a little larger. And so the solution to this kind of riddle is that you have to, if you write this formula with the letters again, you say, okay, you have your voltage U, and your resistance R, which was 1000. And then we already seen that to get the current, you have then U divided by R. And then after that, what we always did was, once we had the current, we then got the power by multiplying the voltage U by I. And so it's U times I. And now if you take these two together, you see that you can substitute. So you have P is U times I, and we start with that. P equals U times I. Okay, I. But now for I, we set here this I is U divided by R. So we just write it different. We do not write I, but we write U divided by R, because it's the same. This one equation is the same. So U divided by R. And then you know U times U, basic mathematics, you see that you have U squared divided by R. And now here is the solution to the riddle. The power P, you always take U to the square and then divide by R. This means if you double U, then the power gets 4 times bigger, and not double as big. And so what we want to do now, so we can, with arbitrary numbers, we can now use this formula. You can always use this formula with a resistor. Let's say we had 10 volts, then we would just say the power, so the 10 volt case, the power is 10 volts squared divided by 1000 ohms. And then this would be 100 volts squared divided by 1000 ohms. And as you know, I just write it out, 100 volts squared divided 1 ohm is just a volt divided by ampere, so that's a little bit of unit calculation. We write ohms as volts divided by ampere, and this then equals, so 100 divided by 1000 is a tenth, so you're already right there, and then that result. And we do the unit calculation. So if you divided by V over A is times A over V, so we have V squared times A divided by V. And then we end up with a 1/10 and 1 volt cancels out, and it is left here volt times ampere, and that is 0.1 watt, because volt times ampere is watt. And then that is, what is a 1/10 watt ton is 100 milliwatt. So 100 milliwatt is well below, so we can still apply our 10 volt to our 1 kilo ohm resistor and still have a sane watt value that is below our 250 milliwatts that we can go into. So the question is, what is the critical voltage level? And for this we can also do a little bit of mathematics. If let's say you want to know O critical, U crit, what is it? And so if we have the formula P equals U square divided by R, and then we know that U square equals P times R, and since there is only positive voltage, so we only looking at voltage in one direction here. We could also say negative voltage in the other direction, but it would just complicate things unnecessarily. And so I should say the solution of this is then so if, let's draw this in this direction, if U is the square root of P times R, then we have solved for our voltage here, and we'll just put in some numbers. So our critical U critical is the square root of the 0.25 watt, so the 250 milliwatts, and times the 1000 ohms. And as you know, a quarter times, so this is a quarter times 1000, so this is 250, and watt, so we write this under the square root, so we have here 250, and then watt is volt ampere times the ohm is volt divided by ampere, and then we have the square, so we are left with what is under the square. Ampere cancels out here, then you have volt square. If you take the square root of volt square, you end up with volts after the square root, and in the square root you still have your 250 volts. And so what is the square root of 250? So it's 15.811 something. And if we want to be safe, we'll say, for example, don't go over, so this is bigger than 15.8 volts, so we could say don't go over 15.8 volts here. Yeah, and that's the whole thing. So we have this 1 kilo ohm resistor, and I wonder if anybody of you ever have thought of this. Hey, I have a 1 kilo ohm resistor, I can go over 15.8 volts. So we could, at the last time of the video, the last thing we could do is to just to make a check what would be with when we insert 15.8 volts, what kind of wattage would we get out. So we say P equals U square. So let's say U square divided by R, and this is in this case, so 15.8 volts square divided by 1000 ohm. And we saw that the units are good. We end up with what? And I just put in the numbers in the calculator. And we end up with 0.2496 494 watts. And this is very close if you round to the third number, third digit after the comma. You end up with being already very close to, or almost there, 250 milliwatts. So I hope you liked the video and you know now what the watt rating on resistors is for, and that it really affects your circuits. Thank you and bye.